So now we find either way. Okay, so yeah, so just wanted to brush off probability. I don't know what in particular you saw. Sometimes you see this as part of discrete mathematics, at least some basic things, but some other things that are equally important may be left out. So for sure, the first concept that we have to talk about is that of probability space, right there. Yeah, so we're just brushing off on probability notion. So what is a probability space? First of all, it is composed of a set omega, right, that contains all the possible outcomes, right, and or a certain experiment, and then so this is the outcome space, and then we have a function probability that takes these outcomes and assigns them a probability value. Right, so we say in general that this goes like into R, and so certain probability happens with a certain outcome happens with a certain probability. There's going to be a real number. Okay, so in fact, for a given outcome, say omega, that is mapped to a certain number here. And basically we have the probability of omega corresponds exactly to like the probability that outcome happens. Now, of course, sometimes in like the informal way of thinking about probability is like, oh, you have like 50% chance or whatever of happening. That's not mathematically very rigorous, or in the other way, it is, but it is not accurate. 50% is just a measure of like portion out of a total. And in probability theory, we like to use numbers between 0 and 1. So we use real numbers, but really between 0 and 1. So this number is between 0 and 1 for all omega. Okay? So a probability of 1 means that this is a certain event that happens with probability 1. You would think 100%. And probability of 0 is the impossible event that never happens. Okay? So it happens with probability 0. 0%. Okay, so here, for example, if we consider the simplest experiment of all in probability, this is defined to be what's the simplest experiment you can think of?
Coin flip?
Yes, tossing a coin, exactly. That is like the paramount example. Then basically omega is the set heads or tails, right? And in fact, let me say that this is heads or tails, but it's just two elements, right? So we can really think of this as like 0, 1. Yes? So this is used, and the reason why it's so important is not only because it's the simplest one, but also because it models bit flipping. Yeah, so you can use it to simulate a lot of stuff. Normally, for example, when you say sample a random bit, what people really actually talk about in the lingo is like, oh, flip a coin. Okay, even though you're actually, talking about generating a random bit on a computer. So it's a very important example, and assuming that this is a fair, unbalanced, fair balanced coin, then the outcomes are equal distributed, right? So they have both probability 1/2, which again is what is commonly known as like 50%. Okay. Okay. Another extremely popular example that is used more for, I think, exercise or example purposes rather than actually to simulate stuff is rolling dice, of course. And by dice we mean 6-sided dice. If you're a gamer, you know that there's other types of dice, but basically, again, it models a probability in which all the outcomes are equally distributed. So if you're rolling just one dice, right, then your space is like 0 to 6, right? 0 to 5, or like 1 to 6, or 1 to 10, or whatever. But the interesting thing is that, like you do for games, you roll more than one. And then it's interesting to analyze the probability of different outcomes that can be, well, we'll get there. But basically, okay, suppose that you roll 2 dice, which is perhaps the most common occurrence. Then you define the set of outcomes as pairs, right? N and M, such that n and m are, say, integers, and they are like between 1 and 6. I would say this is the most common scenario in, say, a lot of board games and other things. You just roll 2 6-sided dice. Okay, so this is already a lot more interesting because we can define a bunch of different outcomes. Okay, so each possible outcome is equally likely, right? And so we have the probability of omega is in fact equal to 1 over 36. Okay, for each omega, in this case omega is a pair n. Okay, so let's see a couple of examples now to start counting. So suppose that you have, for example, an urn, right? An urn. It's my poor excuse of drawing, where you draw from a pot, and it contains like 100 balls, and you're drawing things out, and then say that 21 are white and the rest are black. So what happens if I pick 10 balls at random? I haven't specified here exactly what it means at random yet, but we'll get to that point. Right? So I draw 10 of them out without replacement. Replacement is one important discriminant, of course, in these kind of experiments. And so what is the probability of, say, exactly 3 whites? Okay? For example, this is a natural question to ask. Okay. For here we have to start counting. And normally what we do is we have a total number of selecting balls. Right? We are picking up 10 balls out of 100. Now, according to your combinatorics, that is 100 choose 10. You've seen before this binomial, right? You've seen it in other stuff, for example, in counting polynomials and other things, right? But this is, it's like n over n choose k, which is n factorial, k factorial, n minus k factorial, okay? So this is counting the number of selections, combinations. So the way of selecting k objects out of n. And in fact, you really read n choose k, because you're choosing k objects out of n. So, obviously the monomer coefficient is present everywhere in probability. So in our case, we have 100 choose 10 total ways of picking, right? And then we have 21 choose 3, because we want exactly 3 white balls. And then we have the rest, which is 79 choose 7. Okay? And so, in fact, the total number, we have this number times this number ways of choosing, right? Because we pick any 3 of the 21 white balls, and then any 7 of the 79 black balls. And these are the total number of ways of picking my combination that has 3 whites and the rest black, and I divide it by the total. Yes, because that is the total number of choosing any 10 balls, including 2 white and 8 black or whatever. So this is a first example of how we compute this kind of probabilities. Then we just compute these binomial coefficients, and we get something like 0.223. Okay, remember that my probability is defined as a number between 0 and 1. Okay, so now this was a simple event. What is really more interesting is to compute the probability of compound events. Okay, and so when you think about the sample space, right? This guy. You have a bunch of outcomes in there, right? And they're all distributed. Like, for example, if you take the dice, you have 1 6, 2 4, 3 6, like depending on what's the face on, say, the black die and the white die. But what is interesting is not to evaluate the probability of like a certain outcome occurring. For example, in the case of the two dice, we said they all have same probability, right? But to evaluate an outcome that is a subset, a proper subset of this space. You agree? In fact, this is the principle on which all the games are based. So if we want, for example, to roll two dice, normally we want to accomplish not an exact result, but an outcome that is, for example, oh, the total has to be bigger than. Okay, in which, for example, you can model like n plus m greater or equal that. Okay, or whatever, like the two dice are equal, like you want doubles or whatever. So you have a bunch of ways of defining outcomes, right? And so, for example, we may be interested in the probability that like at least one of the dice shows a 6, because a 6 is a success. Okay, and so what is this event? Then this is comprised of 1, 6, 2, 6, etc., up to 6, 6, right? And then 6, 1, 6, 2, blah, 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 up to 6, 5. Okay? So I have like these possible outcomes, they go into this subset, and that's the event that I'm interested in assessing. Okay? And so now, if you know the probability of each outcome, how can you assess correctly the probability of like a compound event? This is important because it's not as straightforward as it seems. And in particular, you have to introduce the idea of independence, among other things, but also of intersection of events, right? And so we can formalize some of this stuff. For example, one thing that we did mention, right, is that the probability of each individual event has to be less or equal 1. Okay? And this is valid for a subset of events as well. And in particular, the sum of the probability of omega for omega in my sample space actually has to be equal to 1. Okay, so when I sum all the possible events, that happens to probability 1, which makes sense because one of the events is going to happen shortly. Okay, so as we were saying, the 0 probability means impossible event never happens, and the 1 probability contains it always occurs. Now, so how do we define an event properly? So this is like really like requirements of a probability space, okay, the basic requirements. Now, how do we define an event? An event is a subset, let's say E, contained in the sample space. Okay, and how we define the probability of an event occurring? Well, it's just the sum of the probability of omega for omega in E. Okay. And in particular, we have two extreme cases, of course. If an event is impossible, I can think that this is the empty set, in which case the probability is 0. So the probability of the empty set is obviously 0, and then the probability, in fact, of the whole space, yes, which is equal to 1. Okay, so if my event is empty, so like, what's the probability that one of the faces of the dice is a 7? None. But if my event is the entire space, then it's probability 1. Okay, so this is like a simple convention. Okay, now we get into a little bit more interesting things. Keep in mind this example here, right, where we want that at least one face shows a 6, and you can already see that we have an overlap here, right? Because first we listed the second dice being a 6 and the first being whatever, that works. Or we could list the first dice being a 6 and the second being whatever, but of course we have a case in which both dice show a 6. And what you don't want to do is to overlook this one, count it twice, right? So we have to talk about events that are disjoint. And again, you've seen disjoint when talking about sets, for example. Right? So what does it mean the two events are disjoint? That the intersection is empty. Now, if two events are disjoint, then everything is quite easy because we can consider the probability of E union F Here, keep in mind that I'm talking purely as sets, right? This makes things easier. So E union F is if I take two events and I combine them together, right? And as you know from set theory, if the two events are disjoint, then the cardinality of E union F is just cardinality of E plus cardinality of F, right? So it makes sense the probability of E plus probability of F. Right? Because I have certain amount of events in E, certain amount of occurrences, outcomes in E, certain amount of outcomes in F, and so if I take them together, it's just a sum. This is if the events are disjoint. Okay. If the events are not disjoint, then this formula is not accurate anymore, and you see already in this example here, these two events, you have to be careful because you want to subtract the occurrence in which happen more than once. Yes. So if the intersection of the two events is not empty, then we have to subtract the probability of the intersection. Okay. And if this is empty, this probability is 0, so the formula is still valid. Okay. So this is the generic formula, which you may have seen already in some algebra courses, for example. Now, another important idea is that of a complement, of course. Again, set theory helps greatly because what is the complement of a set? The rest, right? The total minus that. So we can, for example, write E complement or E complement like this, and I prefer the notation with the bar, although your book uses the little index C, which is not my favorite. But anyway, what is this? It's the set of outcomes omega that are not in E. Okay, very simple idea. And why do we care? Well, first of all, it makes sense that if I have a total and I subtract a certain part, then the probability of the complement is the probability of the total minus that one, which is going to be, so the probability of E complement is going to be 1 minus the probability of E. And this is really like one of the most important things in probability. Probability of the complement is 1 minus. And you care about this because in a lot of cases, it's easier to evaluate the probability of the complement rather than the direct probability. Okay? Let's go with a couple more examples so I can clarify what I mean. Everything clear so far? We're just brushing off, but this is important. Okay? So we go back to actually let's stay on this because that's the example we want to use. The probability of rolling at least one dice. Okay? Maybe we can do this because I don't want to write that set again. Okay. So now we can think of this as an event, right? So we can say, oh, this is E equal that. And that's exactly the event of rolling at least 1 6. What is the probability of this event? Well, I have, if you count the 11 outcomes in there, right? And each of these 11 outcomes have probability 1 over 36. So the probability of E is 11 over 36. Makes sense? I just count them. In this case, I can do it explicitly. So now, what is the probability of not rolling at least a 6? So if you're playing a game, how likely are you to fail? Well, then the probability of not rolling a 6 would be the probability of the complement, and this is going to be 1 minus 11 over 36, which is 25 over 36. Okay. This is again a very simple example. Now, let's consider a different event. For example, F to be no number bigger than 2. Okay? Actually, bigger than 2 is strictly bigger than 2. Okay? So say that I roll at most a 2 on any face. Okay? Well, then F is given by the following pairs. This we can write all. Obviously 1 1, 1 2, 2 1, and 2 2. okay? So if I fail, maybe this is like, okay, feeling like really bad, okay? I'm gonna talk about this imaginary game that we're playing. Now, of course, the two events you can see from the set, in terms of sets. Sometimes, in fact, I was saying most of the times you can't write the sets explicitly. Like you have to think about it. But like in this case, you can actually see explicitly that the two events are disjoint, and therefore the probability of, say, either rolling a 6 or otherwise failing really badly, say not rolling bigger than 2, it's going to be probability of E union F, which is probability of E plus probability of F minus probability of E intersection F. This is equal to 0 because the two are disjoint, and so we get this one, which is, we said, 11 over 36, plus this one, which is 4 over 36, so 15 over 36. Right? Very easy. Now, this is because the two events were disjoint. What if I consider another event, for example, doubles, which is, of course, all the pairs 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So there are 6 of them. Now the two events are not disjoint anymore. So following the same rule, we count 11 over 36 plus 6 over 36 minus the intersection, which in this case corresponds exactly to the pair 6, 6. Right? So 1 over 36. So it's not 11 plus 6, 17, but it's actually 16 over 36. Okay? So if I consider PR of E union G, we get 11 over 36, that's E, and then 6 over 36, that's G, and then that's the intersection. Okay, so hopefully this clarifies, right, why it's important to consider whether the events are disjoint or not. Okay. Now here is an example of why we care also about the complement. Let H be the event that the sum is at least 4, the sum of the two dice. Right? Well, then of course you could compute this directly, right? But you would need to like compute a lot of stuff. I think it's easier to compute the probability of not H, right? Because the probability of the sum not being at least 4 means that the sum is like 3 or less, and there's only 3 outcomes, right? Not H is the event 1, 1, 1, 2, or 2, 1. Everything else is sum at least 4. So then we can do this quickly, and this is just 3 over 36. Right? And then therefore the probability of H is 1 minus 3 over 36. Okay? So a lot easier in this case. So you get 33 over 36 or 11 over 12. Okay? So what we're seeing is that this gives me a union which is in logic the OR, right? And so therefore the intersection of two events corresponds to the AND. Okay? And I'm saying this because so far we've been talking, of course, about sets and we like write out all the dice and whatnot. But of course, in real experiments, you cannot consider that. So we need to know what this stands for, right? And this is the bridge between set theory, logic, probability, and so the probability of the intersection of two events means that both happen. That's why you have an intersection. Okay, so this is not necessarily always a straightforward function, as we've already seen. So we've seen the case of a coin, the case of dice. There is a third paramount example in probability. I can probably take this away now. And that is drawing cards. Okay. So not, it's not a coincidence. All these things are the gambling things, right? So, okay. So when you draw cards from the standard deck, normally this is like 52 cards deck with say 4 suits and 13 cards per suit, marked from 1 to 13, the usual setup. So let's consider two events, E and F. E is like first card, P is king. King is 13, right? and then this one in the second card is king. So I draw 2 cards, right? And then the second card is drawn without replacing, right? So if I have no replacement, let's see what happens, and then let's see what difference I get if I do replace a card. Okay? So clearly, I'm drawing the first card. The probability of E is 1 over 13, because, well, it would be 4 over 52, right? So it's 1 over 13. I have 4 kings in the deck, one per suit, so this is equal to 1 over 13. So this is easy. The probability of drawing a king in the first card is 1 over 13. Now, what happens to probability of F? Well, that's the same, right? That's also probability of F. Well, in fact, so if I don't know, so this is only true if I don't know anything about the first event. Right? But if I do know that E has occurred, then I don't have 4 kings anymore. Actually, I have 3 kings only. And so we have to make a distinction in the case where the E happened or not. Okay? Because this considerably changes my probability. So in the vacuum, the probability of E and F is the same. But this is not the case in practice. Right? And so what we have is that the probability of F, if E occurred, it's actually less. It's like 3 over or 51, right? Because I took that first card out. But the other one, probability of F if E not occurred, then that is 4 over 51. And so look at this, is interesting, right? If F happens after E and E occurred, so if I did draw a king, then the chances of drawing another king are actually lower, because I have like 1 less king in like more or less the same amount of outcomes. But if I didn't draw a king, then my chances are actually higher because my total space is like 1 less. Right? So this is really important. It's a really important distinction even in this very simple experiment. But now, of course, we have to consider the case precisely. In particular, if I'm looking for a probability of drawing 2 consecutive kings, so E happened and F happened, then this consists of E intersection F. Right? And this is smaller than the probability of the 2 happening independently, because I have to consider whether E happened or not. In fact, this is not probability of E times probability of F, but it is probability of E times the probability of F given E, by which we mean this one, given that E occurred. Okay? Because of course I have to, if I want 2 kings, I have to assume the first one did happen. Okay? So in fact, in this case, I get 1 over 13 times 3 over 51. Okay? Which is 1 over 2 to 1 or 0.0045. So that makes you realize how hard it actually is to draw 2 kings. Okay, now let's consider the event. Second card is an ace, so the 1. Now the things are different because, of course, the occurrence of E makes G more likely, but actually, if we know that E occurs, so now we have the G is 4 over 52 also, but it becomes 4 over 51 if a king is drawn. Okay, so that's the difference between the 2. Okay, because we're not using the same card. So we have either 4 over 52 if E did not occur, or 4 over 51 if we actually draw the first one. So now, of course, this was in the case where we had no replacement. If we do get a replacement, so if we draw a card then we get to put it back, then obviously the probability is the same at each step. And in that case, then we do get the probability of E intersection F is equal to probability of E times probability of F with replacement. Okay. That is not common with cards, but it is, for example, common in other scenarios, like when you toss a coin or you roll a dice, if you roll a dice one after the other. Right? So that would be, in our case, 1 over 13 squared. So the probability of drawing two kings, if I'm happy to put it back, this turns out to be like 0.006. So that's better, right, than the 0.0045 that we had up there. Okay, so what we learned is that the probability of one event is not isolated in the vacuum, but it depends on other events that may have happened before that. And we already kind of had an intuition about independence of events, which is important. So we're going to elaborate on that. And we can say that E and F are independent. What was the scenario for independence? That the probability of both events happening is their product. Mm-hmm. And that's how we like to define it, is probability of E intersection F equal probability of E times probability of F. In other words, it means that this probability of F given E is the same as probability of F. E doesn't affect that outcome. Okay. So again, as I was mentioning, this is the example with like coins. Right? Remember that a coin is tossed with probability 1/2 every time. So if I have, say, the first event E1 is I tossed a coin 10 times, or I tossed 10 coins, it's the same thing. Yes. E1 is like I get 5 heads. Say in the first 5 tosses. Okay. Or I could have E2 to be first 5 heads, then 5 tails. Clearly this event is different from E1. The first one is I just want 5 heads and then I don't care. This one is I want 5 heads and then 5 tails. And then I actually have an even different event, which is I just want exactly 5 heads. I don't care when. All these events are similar but different. Okay? And let's see what happens to these. So the easy one is tosses are independent. Okay? And this is the same for like rolling a dice or any other kind of like experiment, which is why it's funny that sometimes they think like, oh, this die like rolled a 1, so next time it's gonna be better. Right? That doesn't make any sense because you're just as likely to get another 1 as to roll a 6, right? So, but superstition sometimes defies probability. So anyway, so because tosses are independent, the first event is easy to count because I just want 1/2 probability of getting ahead 5 times because I want 5 heads consecutively. Mm-hmm. The rest I don't care. So this is just 1/2 to the 5, right? This is 1/2 times 1/2 times 1/2 times 1/2. This is because the events are independent. So it's 1 over 2 to the 5. So it's 1 over 3. Okay. So now, what I'm asking in the second event is not only the first 5 tosses, and then I don't care what happens to the other 5 tosses. I want 1/2 for the first 5 tosses, and then I want basically like 1 minus 1/2, or that's the probability of the other one, a tail for the other 5 tosses. So that's 1 over 2 to the 5 for the first one, 1 over 2 to the 5 for the second one. So the probability of the second event would be 1 over 2 to the 10. Okay? So this event is much less likely to happen. This is 1 over 1024, yes. If I want 5 heads first and then 5 tails, rather than having 5 heads and then whatever. Okay? Now, the interesting one is how do we compute the probability of the third event, which is I just want 5 heads. Yes? Because there is no restriction on when these occur, I could get 5 heads first and then 5 tails, or 5 tails and then 5 heads, or I could get 1 tail, 1 head, 1 tail, 1 head, 1 tail. I have many possible combinations, right? And in fact, combination is the key word, okay? So we just need to know I want 5 heads and 5 tails, because I want exactly 5 heads, right? So the remaining ones have to be tails, but they can be in any order. So I just need to count how many possible ways of selecting I have, and that is given by 10 over 5, right? Basically, I choose all my heads occur at toss 1, 3, 4, 5, and 7, whatever, or any other combination of these like 10 places. Once I've chosen that, right, I have a certain probability of happening. So it's basically this probability times that, right? So it will be given by 10 choose 5 times 1 over 2 to the 10. Right? This corresponds to like basically choosing one particular positioning. Okay, this is in fact 252 over 1024, which is 63 over 256, approximately 0.246. If you count these other numbers, that is exactly 0.031, or approximately, I should say. And this, of course, is very small, approximately 0.0009. Okay, it's nearly 100,000. So if you compare this with this and this, you can see how this is much more likely. If you just want 5 heads in any position, then in fact 0.24 is a 25% chance of actually getting that. So it's a lot more than if you want your 5 heads in the first straight 5, or if you want them in your first straight 5 and then you just want tails after that. Make sense? On the other hand, you could say, oh, but this is like 25%. But heads happen with probability 1/2. So why don't I get 50% if I just want 5 heads? Make sense?
Yeah.
And so this tells you what the difference between intuition and reality is.
Yeah.
That in practice, if you want exactly 5 heads, then it's not 50%, because you imagine the heads and tails happen with probability the same. But it's in fact nearly half of that, because you could get like so the way these events are distributed, and we'll see later, it's not like right in the middle, but there's also the case that happens 6 heads or 4 heads, which are almost equally likely, right? And then like they kind of plateau later, so you have to keep those into account. So the case where you get exactly 5 heads is not half of the probability, but it's much less. Because remember that the sum needs to be 1. Okay, very good. So now we can formalize this thing a little bit better, because we did already. So we looked at independence, and this I think kind of clarifies it. But we haven't really talked yet about events depending on previous ones. And so what we were saying about F happening when E happened, there's a precise formulation of that, and it's called conditional probability. Which means the probability of an event happening given that another event happened. And we write it in this way. F given E. So the vertical bar means F given E. F given that E happened. Okay? Of course, because now I have the complement, an important thing to remember is that if I want the probability of F given that E didn't happen, I can just write F given complement of E. Okay? So we'll be using these two things to count things accurately. And we've already seen that this is not trivial. If the events are independent, something happens. If they are not independent, something else happens. And in particular, the probability of F given E or F given not E is different in all other cases. Okay, so this is just shorthand for what we saw before, F given that E occurred. Now, the conditional probability, in fact, can be calculated in a very simple manner, depending on the probability of the events both happening, right? So we can write this is the same as F intersection E, or E intersection F is the same thing, of course, divided by the probability of E happening, okay? And this is really normally what is taken by the definition of conditional probability. And the intuition is this. On the left-hand side, we are assuming that E occurs. So now we're considering the probability of F happening, but not in the entire sample space, but in a restricted sample space. Okay? And so basically what we're doing is that we are computing the proportion of the event F inside E with relation to the probability of E happening in the total space. Okay, so this one, you know that when you take a ratio, a quotient is always a proportion, right? So it's like if 5 students out of 15 are female, then you say, oh, the ratio is 1/3, is the proportion of female out of the total. So that's the same thing, is how many outcomes of F happen in the E space divided by how many outcomes happen in the total space. And that's how we get this formula here. And okay, so that makes sense. Now, of course, I can rewrite this if I just take this on top, just algebraically, right? So I can just write the probability of F given E times probability of E is equal to probability of F intersection E. Of course, this is just algebra, right? But this is the same as probability of E intersection F, right? And therefore, I can expect that I can write this as probability of E given F times probability of F from the same formula. So the conditional probability of F given E times the probability of E is the same as the probability of E given F times probability of F. Now if I put this and this together and I divide by F, I get an important formula, which is the probability of E given F is equal to probability of F given E. Basically, I'm doing the inverse ratio, right? So I have probability of E divided by probability of F. Make sense? You take it from here, you have this one side, this on the other side, you just divide by F, both sides, and you get that. And this is kind of like a preliminary formula, or what is called Bayes formula. Bayes was the English mathematician. Okay, and so this is very important because if you know the conditional probability of one event given the other, we can reverse it and find the other conditional probability. Okay, so it's very important. So sometimes we're going to be using this, and then we have some other formulas that you can derive from this, because of course, as we said before, it's sometimes easy to compute the probability of an event by splitting into a union of these joint events. Right? And then putting it all together. So we get the two additional formulations, which is this. I can write the probability of E. Now that I know what the conditional probability is, I can actually write this as probability of E given F times probability of F, right? Plus the disjoint event of probability of if given not F, probability of not F. Make sense? It's like writing the 1 plus 1 equal 2, but it's important because it looks like we're writing the obvious, but this number is often easier to compute than the total. Okay? So if you're asking, oh, what's the probability of this thing happening? Okay, let's see how likely is this to happen if F happens, and then how likely is it to happen if F doesn't happen, and then we just put them together. It's great that we're able to do this. Yeah. And in fact, we can rewrite Bayes' formula in the following way. Probability of E given F is the probability of F given E times the probability of E divided by that thing that we have up there. Oh, sorry. The probability of F given E given the probability that E happens plus probability of F given not E, probability of not E. Okay, so we can write Bayes' formula, which is this one, but we replaced the probability of F with the previous step. Okay, and this is like the generic version of Bayes' formula. Okay, and it's easy to prove. You have a proof on your book for this. It's easy. But I'm interested in now some applications which may or may not surprise you. Okay, so suppose now that you have two bowls, urns or pots or whatever, and they both contain gold and silver in different amounts. Okay? For example, the urn number 1 contains 10 gold and 5 silver, and the urn number 2 contains 2 gold and 8 silver. Okay? And now you're like, okay, what happens if I first choose a random urn, and then second, what is the probability of getting a gold coin? So I choose a random urn between the two, and then I pick a coin, how likely I am to actually get a gold, right? Because clearly in the first urn, I have a good probability of getting gold, in the second one, not very good. So in total, what's my chance? And you see, this is already a simple experiment, but it requires the formulas that we just introduced, because otherwise it would be very hard to count. So we set the E is exactly the probability of a gold being chosen. Obviously, the probability of E first depends on which urn was chosen. And so we also define F, say, as the probability of F, the urn number 1. Okay? In this case, it's easy. I can just call F urn number 1, and then not F is, I think, urn number 2. Okay, so now I can actually use the decomposition and say that the probability of picking a gold coin is actually, well, by its formula, right? Probability of E given F, probability of F, plus probability of E given not F, probability of not F. And you see now why it's a lot easier to count in this way, because the probability of F or not F, if F is if the urn is chosen at random, is just 1/2 in both cases. Okay. And now, okay, now in each case I can count much more simply. In the first case, I have a total of 15 coins, and 10 are gold. So this is going to be 10 out of 15. In the second case, I have 2 out of 10. Okay? This makes sense now. Remember, all my probabilities are between 0 and 1, right? So 10 out of 15 is between 0 and 1. I put all the numbers together, and I do my computation, and I get 13 over 30, which is approximately 0.433. Okay? So I have a decent chance of picking a gold coin with this. Cool. So this is a nice event, nice application of conditional probability, and explains why we have to consider always independence of events and conditional probability in our mix. Okay, so now, if everything is still making sense, hopefully, what we really care about is, of course, cryptography, because this is our class. So we can already introduce a little example of this. Any questions? No? Okay, so one thing is, now what happens in cryptography is that we have a lot of algorithms that are probabilistic. Okay. And what does it mean exactly to be probabilistic? So that's why we want to refresh these notions of probability, because of course we couldn't possibly define things accurately otherwise. So in fact there are two main types of algorithms, of probabilistic algorithms. This is just computational theory, not necessarily in cryptography, but basically we have two algorithms, and they're both curiously associated with very famous gambling places. So the first type is what we call Las Vegas type algorithms, and the other one we call Monte Carlo types. Okay, and so the two are exactly opposite. And in particular, the Las Vegas algorithm always output 1. Right? So they always succeed, but they may not terminate. Right? Or they may have a different running time. Okay? So in this case, the output is fixed and is always correct, but it may not terminate. Or it may take a variable time. The Monte Carlo algorithm is the opposite. And basically, here is the opposite. So it always terminates, but the answer may not be correct. So depending on what we're trying to accomplish, we use certain types of algorithms versus the other type of algorithms. Okay, so yeah, so the good thing about Monte Carlo algorithms is that the running time is fixed and predictable, but the answer is not. So depending on what you want. So in the second case, then it's important to introduce the idea of confidence level, because the answer may not be correct, but it will be correct with a certain probability. And then what you do is that you fix your running time so that this falls into the confidence level that you want. And this is, again, the opposite of Las Vegas algorithm, in which you're sure to get a correct answer, but you don't know how long it's going to take you to get there, and the algorithm may not terminate or may have like a variable amount of time. So now you think about, like what is most desirable in cryptography. We've seen already examples of some, and we will insist on one of these two things, right? When did we see these kind of things? Primality testing, for example. Yes? Mm-hmm. And in particular, the thing that comes to mind is looking for primes. Okay. So suppose that now we have a set of integers s. Yes. Very large set of integers. For example, the set of integers between, say, 2 to the 1024 and 2 to the 1025, which is like those 4 RSA, or at least one version of RSA. Yes. And now let's fix an interesting property A. Yeah, property A, since we're looking for primes, could be the property of X being composite. Okay? Then, basically if you're looking for primes, you're looking for numbers that do not have the property. So like prime not J. Yeah. A is just easier to write. Now calculations. Okay, so now, for example, what is one test that we did? The easiest one that we know is the Miller-Rabin test, right? Miller-Rabin. This is a Monte Carlo algorithm, right? Because you don't know if the answer is going to be correct or not in one case. So let's be a little bit more precise. Let's take an integer. Here I call it x. Here they use m. But anyway, let's say that m is an integer in my set, and I want to know whether m has property A. And what you know, and we kind of did that, you can count, or you know that approximately many of the integers in S have this property. That's the case for composite versus prime numbers. For example, oversimplifying, you may know that, like, say, 99% of S has property A, right? And only 1% doesn't have property A. In our example, like are the primes. This is not exactly like that, but it's a simplification. Okay. So if I'm looking for like an absolute certainty, like a Las Vegas type algorithm, it may be difficult, right, to actually certify that. But what we can do is that we can settle for an algorithm that is faster, even though it's not absolutely certain to be correct. And so basically, this Monte Carlo algorithm for property A takes as input this integer, and it takes a randomly chosen number R, right? And returns either yes or no, depending whether these are so the rules are the following. If algorithm returns yes, then M has A for sure. Okay? If the algorithm returns no, sorry, that is not what I meant to say. Let's do one thing at a time. If the algorithm returns yes, then M has A for sure. But if M has A, then algorithm returns yes for, say, a certain probability of choices for R. Okay. For example, this could be, I don't know, 50% of the time. Okay, let's assume it's 50%. We've seen that in Miller-Rabin, actually, this is closer to 75%. Yes? Remember, we said it was the 3/4 for Miller-Rabin. But okay, so basically, we can formulate these two as probability property. So the probability of M has A, given that algorithm equal yes, is 1. Yes, that's the first property that we want. Yeah. So if the algorithm returns yes, then M has the property.
Right.
When you think about it, remember, if that corresponds to finding a witness.
Yeah.
So if the algorithm returns it's yes, it's composite, then you know it's composite.
Right.
Because you get a witness. Now, what's the probability? The other one, that the algorithm returns yes, given that M has A, so that's not so sure, right? This, let's say, for example, at least 1/2.
Okay.
Okay? Because there are those things such as like pseudo-primes and other things. So the algorithm could return yes, it's composite, but in fact, that's
It's like B prime.
so now what happens if you run your algorithm, say like n times, right, on the same integer, and you use different randomly chosen value for your randomness. So this is, I'm formulating it generically. This depends on the test you're doing. In the test of Miller-Rabin, you choose like different bases, right? Remember, so there is like a random component, of course, because these are probabilistic algorithms, right? You choose a different randomness every time, and you get your outcome. And so basically what happens is, we've already seen this, right? If a single trial returns yes, then we know that M has property A. Okay? Because this probability is 1. But we may be extremely unlucky, but actually in our case this is good, like this is what we want, is that there is not even a single occurrence of yes. They call the tests return negative. So it's like the first test return negative. Oh, maybe it doesn't have A. Right? Then the second test does it, and then you do it like n times, and in the end all the tests are negative, then you can be quite confident that M doesn't have A. Because your probability, basically what we can do, we are trying to estimate what's the probability of M does not have A, given that algorithm equal to no n times. Okay? Because once I compute this, then I have my level of confidence.
Right.
And so, for doing this, that's why we use all the previous notions of conditional probability and independence, right? We can define two events. The first event is M in S does not have A, which is a prime in our case. And then the second event is algorithm equal to no for n times.
Can you move the paper up?
Yep, in a row. Right? So we use these two events, and then you can see that clearly the probability we're looking for is E given F. Yes. So we take the probability of E given F, because we're looking for the probability of finding a prime, given that I find n different results of negative, negative, negative. This is exactly what we're doing with Miller-Rabin test when we described it. So we described it on a very intuitive level, but now we're just trying to formalize it, right, as a Monte Carlo algorithm. And so by Bayes' formula, this is probability of F given E times probability of E. And then we divide by the probability of F given E, probability of E, plus probability of F given not E, probability of not E. Right? That's the formula that we saw on the previous page. We replace probability of F here at the bottom with the probability of F given E and probability of F given not E. Right? And now we can compute all of these pieces individually, right? Because we have all the data. So we count a proportion. We say that oversimplifying, 99% of S has the property.
Yeah.
So if E is the probability of M, E is the event M doesn't have the property, then the probability of E should be 1%, right?
Mm-hmm.
So it's 0.01. And the probability of not E should be 0.99. Right, that's the first one.
Yeah.
Now, again, this is a simplification. What we did instead, we counted the numbers, so we had those interesting theorems that count like what's the proportion of primes in the. But this is just for ease of calculation, right? Okay, now let's move. So we've done E and not E. Now, what's the other pieces? What's the probability of F given E? Okay, that's the last piece of the puzzle. So F given E is possibility the algorithm outputs no, given that M is a prime. So now, okay, so if M doesn't have if M doesn't have the property, which is our assumption in this, then the algorithm always needs to return no, because by the first property of Monte Carlo, if the algorithm does tell yes, then I have to have the property. So it's the contrapositive essentially, right? And therefore, basically the probability of no given not A, just to write it very compactly, is equal to the probability of A given yes. And so that's 1.
Right.
Okay? And therefore, when we compute probability of F given E, F is algorithm equal no n times in a row. That would be 1 to the n.
Uh-huh.
And so that's 1 again.
Yeah.
So this probability of F given E is just 1 again. Okay? Now the last thing that we need to compute is this piece, which is the probability of like a false positive, right? So the thing is, we run the algorithm n times independently. The different times and different bases are not related to each other, right? So I run the algorithm n different times, and this is where this probability comes into play, right? And so this is the probability of F given not E is the same as the probability of a no given the M actually is a composite number, right? And I do this n times. I'm taking the power of n because the events are independent, so I'm doing this times this times this times this n times. Yeah. So what's the probability like of faking it? Essentially, But now this is easy to compute because it's to the power of n, 1 minus, right, the probability of yes given A. Yes. And we know that this is basically 1 minus 1/2 to the n, right? If it is exactly 1/2, otherwise this is a less or equal, yes? If you say my probability is at least 50%. Okay? So this probability is at most 1/2 to the n, or 1 over 2 to the n. So this probability is bounded by 1 over 2 to the n, and if you can see that if n is big enough, this is why we want n big enough so that this probability gets really, really small. Okay, so of course, if I test just once, I could be unlucky. But if I test many, many times, then I have a pretty good confidence. Now I can just chuck this, and this all into my formula, my base formula, and in fact I get, because here I have a less or equal, that the probability of E given F is, I just put all the numbers in there, 1 times 0.01 divided by 1 times 0.01 plus this probability is 2 to the minus n times 0.99. When I compute all my things, then this simplifies to, after some algebra, 1 minus 99 over 2 to the n plus 99. So my probability is basically 1 minus a certain factor. Right? Now, if I take only 1, n equal 1, if I just try once, this number is very close to 1. Right? It's like 99 over 101, essentially. So I have a very small chance of succeeding. Right? But you can see asymptotically that when n grows, then this 2 to the n really dominates, and this denominator gets really big, and then therefore this number gets really small, and my probability is closer and closer and closer to 1. So in this way, you actually have an explicit formula to compute my desired level of confidence, right? The one we did back at the time with Miller-Rabin was kind of hand wavy, right? But in this case, I can actually compute it exactly. For example, what happens if I run the algorithm n equal 100 times, right? Then I can actually compute, more or less exactly. If I put 2 to the 100 here, right? And then I get that my probability is approximately like 1 minus 99 or blah, 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 which is like 1 minus 10 to the negative 32. So I have like a good interval of confidence. And so in most practical purposes, this is why it's enough to say like run the algorithm 100 times, and then you can be pretty sure that this number is prime. Okay. So this is an analysis of Monte Carlo algorithms, which we've seen a lot of, and other. For example, we have another test, which is the Solow-Strassen algorithm, which is also Monte Carlo, and has a different setup, right? But it responds to the same set of rules with just different odds, different chances of being a fake and whatnot. So if you look back at that lecture, you will see. So now we've introduced Monte Carlo algorithms. Of course, we do have Las Vegas algorithms, right? We also talked about this these tests that return like the AKS pragmatic test. But in practice, things like Miller-Rabin always win for practicality.
Yeah.
Okay. So it depends on your situation, but now at least from now on, when we talk about probabilistic algorithms, we can always say, oh, this is a Monte Carlo algorithm like this and this and this parameter, right? And then next time we can talk a little bit more about random variables and distributions probability and expected values, which is kind of what we want to understand a bit more collision attacks. Okay. So we can give a little introduction here. We have 10 minutes. Do you have any questions so far? Okay. The next time we can keep going with this. So it's a very condensed refresher of probability, but it's fascinating, and I think this is my personal experience that if you do get into things like cryptography and your probability background is not strong, then you kind of struggle to understand certain phenomena, right? Okay, so now, rather than the experiment itself, sometimes you want to see what the consequence of an experiment is. And so mathematically, we're interested in a function that is defined on an event. Okay? And this is exactly what a random variable is. Very fascinating name. I love random variables. Very fascinating. So what is a random variable? It's a function x that goes from omega to r. So the domain is the sample space, and the output is a set of real numbers. Okay, so the random variable can take only finitely many values, of course, because our sample spaces are always finite. But we can always represent the values as real numbers. Right? So we can always use these random variables to define events. For example, any real number x defines at least 3 interesting events, right? So the probability, the first one is given omega in omega, the random variable in omega is like less than x. Yes? Or say less or equal. Then we have the equal case, and then we have the greater case. Right? So for example, if we fix a certain target x, we can count the event such that this variable is x of omega is like less than x, or that is exactly equal to x. Or so think about the dice, right? For example, like, oh, this is exactly equal to, what is the random variable? For example, the sum of the 2 dice. You say, oh, the sum of the dice is like equal to 5, or less or equal to 4, or something. So yeah, so that sum of the 2 dice is a very easy first example of like what a random variable is. Okay? Because remember, in the case of dice, omega is like a pair nm. So x we can define as like n plus m. Cool. So let's say x takes omega, which is like nm into n plus m. Cool. And then we can fix like these kind of 3 very simple. Of course, we have like more complicated, right? Okay. So once we fix that, and we'll see examples. What is now we want to understand the probability of these events, right? And so we introduce what is called the probability density function. And density is the keyword here, and we call this fx of x. This x is your capital X, the random variable. This is your element, okay? And we call, so maybe let's just use this, let's just call this like P, okay, or something else. Then this is defined as the probability of x equal P. So in your book you have little x and capital X is a little bit harder to write. Okay, so fx of P is the probability that the random variable takes exactly that value. Okay, so sometimes we just write f of P, or in the notation of the book, f of x, if we don't have to specify what the random variable is. Okay, and so now you can use the distribution function of f right, and this is defined as, let's say, capital F of x, which is the probability that x is less or equal. This sometimes is preferable instead of the density function. Okay, and so this is actually a fundamental notion, the distribution function of a certain random variable, because it gives you the occurrences like bounded to a certain value, right? In our case, these two are very close because they are all finite and discrete, but in case of continuous variables, that's not the case. Okay, so having introduced this, we can. So now this all sounds very theoretical, but we have already seen at least I think, two distributions that are super common. The first one is what we call the uniform distribution, and a lot of times I may have said, like, choose, for example, uniformly at random, or that means random according to the uniform distribution. The uniform distribution, we can define it formally. If I have a set S that contains n elements, so for example, like 0, 1, like n minus 1, then the random variable given f(x) of j is the probability, remember, that x is equal to j, is defined exactly as 1 over n if j is in S, or 0 if j is not in S. Okay? This is more a sanity check, but in general, what you care about is that for every element of the set, the probability of the random variable taking that is exactly 1 over n. Well, this is the case, for example, of the coin, 1/2, or the fair coin anyway, the single dice, right? And so on. So uniform distribution, then we say that the random variable x is uniformly distributed, right? Or follows the uniform distribution, or whatever. This is the 100% most important distribution you will get from probability, which is crazy, right? It's the simplest one. But what you really want, in a lot of cases in cryptography, is to take objects that are distributed uniformly at random, because of course that leaves you the most uncertainty, right? And if every element is distributed equally, right? And if you're faking it, like is the case for example, a public key, right, which is not a random element, they want to look like a random element, then you want this to be distributed as close to the uniform distribution as possible.
Yeah.
And in fact, I would say that even more than for public keys, for things like ciphertext, right? Remember we talked about indistinguishability of ciphertext? How can I guarantee that my ciphertext is indistinguishable? But if I can prove that my ciphertext is distributed uniformly, then of course the best thing an attacker can do is guess.
Right.
Okay? This is ideal. In practice, I can often not prove that my ciphertext is distributed uniformly, but it's close. Another one that is the last thing that we'll see today, and you may have seen already, is the binomial distribution. The binomial distribution is also relatively simple. So basically, I have two events: success or failure, right? And let p be the probability of success, and then failure would be 1 minus p. Okay? And the experiment is performed like n times, and the random variable x is number of successes. Okay? And then, of course, if we fix our attention on, say, k particular experiments among the n, then the probability that exactly those are successful will be given by p to the k minus 1 minus p to the n minus k. Okay? This is the core of the binomial distribution. Why is it called binomial distribution? Because we have n choose k, right? Ways of choosing k particular experiments. For example, the first k, or the last k, or the first, the second, or like, okay? And then the probability of having exactly k successes is the density function evaluated at k. So it will be f of x of k equal the probability of x equal k.
You're off the screen.
Yep, sorry. And this is in fact going to be exactly n choose k, p to the k, 1 minus p to the n minus k. Okay? And this is called, in fact, the binomial density function. Okay? So the binomial distribution, you see, is another important distribution that occurs proportionally to the number of successes and depends on the value of p, for sure. For example, if p is 1/2, then p and 1 minus p are the same thing, right? If you're tossing a coin. But in other events, the success could be happening with only 1/3 of the chances, and then in success. So this is for the cards, right? And when we count cards like now, the main probability is like 1/13, and then the other one is, and then this probability becomes more and more interesting. In general, when we do this, this parameter p is important, of course, and then depending on the number of trials, I have p to the k and 1 minus p to the m minus k. And of course, I have to consider how many ways I have to choose my k successes among the, this counts the probability of having exactly k successes among n experiments. So it's binomial. Okay, so again, this is kind of something that we've already seen before. We will expand on this in next lecture because we have other important distributions, and then we can see like how we use this for. Okay. Cool. So this was all for today. I'm gonna stop this.